Welcome to This Explainer. Today, we're going to uncover a completely fascinating geographical mystery. We're talking about how our wildly spinning planet actually manages to maintain its physical balance.
So let's dive right into this puzzle. Think about it for a second. Despite rotating at incredible speeds and having this drastically uneven terrain, you've got towering mountains reaching into the sky and then ocean trenches plunging way down into the abyss, the Earth remains remarkably stable. How on earth does a sphere with such a crazy uneven distribution of weight not just completely lose its balance and tip over?
Well, this stability is exactly what American geologist Clarence Dutton defined back in 1889 as isostasy. It's a great word. It's derived from the Greek isostasios, which literally means in equipoise, or what's also known as samasviti. Basically, it describes this absolutely essential state of mechanical equilibrium across the Earth's crust. It's the hidden mechanism keeping our world perfectly physically balanced.
All right, so here's our roadmap for this explainer. We'll start with what isostaticity actually is, then look at early gravity surveys, dive into Airy's root theory, Pratt's level of compensation, Joly's zone, and finally wrap up with Heiskanen's combined theory.
Okay, part 1. What is isostasy, and how does it balance the Earth?
Imagine passengers on a moving motorcycle. If a passenger shifts their weight, the bike kind of jerks and readjusts to maintain perfect balance, right? Well, that brilliantly illustrates the concept of isostasy. The Earth essentially does the exact same thing. When natural forces like erosion strip away mountaintops and dump all that heavy sediment right into the oceans, the massive weight distribution of the crust changes. So, to prevent the entire planet from totally destabilizing, the Earth physically adjusts itself. The crust under the heavy oceans sinks deeper, while those lightened mountains literally push back upward. It's like a giant seesaw.
Moving right along to Section 2, Gravity and Initial Surveys. Let's talk about finding this missing mass.
Before we had all these answers, early scientists started noticing some really bizarre clues hidden in the Earth's gravitational pull. These foundational geodetic surveys revealed surprising gravity anomalies right near massive mountains. If you track the timeline, starting in 1755 with Pierre Bouguer in the Andes, then fast forward to 1855 with Archdeacon Pratt in the Himalayas, and George Everest surveying the Indo-Gangetic Plains in 1859, they all realized something completely baffling. These massive mountains weren't pulling on their instruments as strongly as the math predicted. It was almost as if the mountains were hollow or just missing incredible amounts of mass.
That brings us to Section 3, Airy's root theory and the idea of uniform density.
So, here's our first major breakthrough. Sir George Airy proposed this uniform density varying depth model. He applied the law of flotation, basically suggesting that the crust floats on a denser substratum, like a heavier, glassy magma layer, just like a massive cargo ship floats by displacing water. In Airy's mind, a mountain isn't just sitting flat on top of the Earth. No, it's a block of uniform rock that sinks way deep down into the magma below to support all that soaring height up top.
And to put an exact number on that, Airy believed that for every one part of a mountain towering above the surface, 9 parts plunge deep below as a massive hidden root. 9 parts! It's exactly like an iceberg. What we see as this huge, towering peak is really just a tiny fraction of the massive structure balancing everything out beneath the surface.
But, as you might guess, this bold theory quickly ran into a pretty glaring geological problem. See, Airy's theory predicted an 80-kilometer deep root for the Himalayas, and critics were quick to point out a fatal flaw. A root that deep would just completely melt in the Earth's intense internal heat. The math worked beautifully, sure, but the actual physical reality of a solid root sitting at that depth, it just wasn't possible.
Which leads us nicely into Section 4, Pratt's level of compensation and the concept of varying densities.
This is where Airy's primary rival, Archdeacon Pratt, enters the conversation. He offered a totally different solution. Pratt proposed a strict inverse relationship between height and density. His role was really simple. Bigger the column, lesser the density. Smaller the column, greater the density. Meaning, the Himalayas aren't missing mass because they have some giant melting root underneath them. They actually have less gravitational pull because the rock they're made of is fundamentally just less dense. It's lighter material. So, we're left with this stark theoretical duality. On one hand, you have Airy arguing for uniform density with varying, really deep roots. On the other hand, you have Pratt arguing for varying densities sitting perfectly flat on a single line of compensation. Pratt believed that at a certain depth, all the weight becomes perfectly equalized, no varying roots at all.
Okay, Section 5. Decades later, someone tries to mediate this whole debate. Joly's zone of compensation.
In 1925, Jomly proposed that instead of Pratt's razor-thin line of compensation, there's actually a 16-kilometer or about 10-mile thick zone of compensation. This is where densities vary before finally stabilizing. I mean, the Earth is a messy place, right? And Jomly realized that the transition from varying densities to uniform stability doesn't just happen on some perfect, neat mathematical line. It happens across a thick transitional band.
And finally, Section 6, Heiskanen's combined theory. It actually took until 1933 for a scientist named Heiskanen to create the modern synthesis of all this. He essentially put Airy and Pratt into a blender and mixed them up, creating this brilliant hybrid model. He concluded that both depth and density vary across different land masses. So some mountains do have deeper roots, like Airy suggested, and some rock is fundamentally later, like Pratt suggested. But wait, there's more. Heiskanen determined that density even decreases with height within the exact same mountain column. Literally, the higher you climb, the lighter the rock becomes. All of these theories collectively prove that we live on what J.A. Steers famously called the unstable Earth. Our planet is constantly shifting to maintain this precarious equilibrium. The crust is never, ever truly static. It's a live, shifting puzzle, bobbing up and down on the mantle right beneath us just to ensure the globe keeps spinning without a hitch. Which leaves us with this absolutely incredible thought to ponder. As you look at the towering peaks and deep oceans today, ask yourself, as erosion constantly shifts billions of tons of weight from the highlands down to the ocean floors, how and where will the Earth's crust aggressively snap back into balance next? The ground beneath your feet might feel completely solid and permanent, but thanks to isostasy, we know it's always quietly preparing for its next big balancing act. Thanks so much for joining me on this explainer. I really hope you found it as fascinating as I do.